There is a render you have probably seen. A city on Mars at dusk. The domes glow from inside, warm as lanterns, and the sky above them is the colour of old brass. A starship stands on a landing pad in the middle distance, taller than any cathedral, its hull scoured clean by wind. Figures in white suits walk between the buildings without hurry. Somewhere, presumably, there is a school. Somewhere, presumably, there is a hospital. A child, in some versions, presses a gloved hand against a window and looks up at a second, smaller sun. The render is beautiful. The render is also, in almost every detail that matters to a human body, a lie. Not a malicious lie. Not a lie in the sense of deception. It is the kind of lie a very determined engineer tells when the problem in front of him is so large that he must, in order to keep working, agree with himself to leave certain things off the whiteboard. The soil in that render does not corrode a lung. The air on the other side of that window does not, within 9 seconds of exposure, vaporize the moisture on a tongue. The dust does not cling to every seal and every hinge and every filter until the seals fail and the hinges seize and the filters one by one give up. The gravity that holds the child to the ground is not slowly unmaking her skeleton. The radiation passing through her body at this instant is not, statistically, planting the seed of a cancer she will develop in her 40s, if she lives to see her 40s, which the mission plan does not, in any honest reading, guarantee. None of this is in the render. It cannot be. A render is a promise, and a promise to survive contact with an audience has to look survivable. This is a documentary about what the render leaves out, not to mock the dream. The dream is old and beautiful and worth taking seriously. It is a documentary about the gap, the specific, measurable, physiological gap, between the timelines being announced from Boca Chica and the biology of the animal those timelines propose to send. Over the next several hours we're going to walk that gap in patient detail. We will visit the soil and the pressure and the dust and the radiation and the bones and the mind. We will meet the instruments that have measured each of these things and the researchers who have spent careers trying to understand them. And we will end, because this is not a story about despair, with the shielding and the tunnelling and the slow, unglamorous work of adaptation that a real first mission would actually require. If that is the kind of walk you like to take slowly, in the dark, with the lights low and no urgency to arrive anywhere in particular, settle in. Let's begin. The daydream, at the scale we are living inside of now, is roughly a quarter of a century old. You can date it, more or less, to the turn of the millennium, when a young engineer who had just sold his stake in an internet payments company began telling anyone who would listen that he intended to die on Mars, just not, he liked to add, on impact. The line is a good line. It has the shape of the man who says it, half joke, half thesis statement, and underneath both a genuine and unshakable conviction that the destiny of the species was to become, in his phrase, multiplanetary. That conviction has not wavered in 25 years. It has only, as the resources available to him have grown, become louder. The timelines have moved. They have always moved. In the middle of the last decade, the target was the middle of the 20s. As the 20s arrived, the target slid to their end. As their end approached, the target slid again. In May of 2025, in a presentation delivered in front of one of his own launch vehicles, Musk laid out a step-by-step architecture that put the first human landing as early as 2029, with an uncrewed lander arriving a synod or two before to prove the descent. By the summer of the following year, the number had softened again into a range. Humans on Mars, he said, in roughly 5 to 7 years, which put the first bootprint somewhere between 2031 and 2033. There was no correction, no admission that the earlier date had been optimistic. There was only the new date, delivered with the same certainty as the old one. You get used to this if you follow the field long enough. The dates are not predictions in the way a weather forecast is a prediction. They are aspirations delivered in the grammar of predictions, because aspirations do not attract capital, and predictions do. Underneath the shifting numbers, the architecture stays roughly the same. A very large rocket called Starship, capable in principle of lifting more than 100 metric tons to low Earth orbit. A refueling operation performed in that orbit, in which one Starship transfers propellant to another so that the second can leave for Mars with its tanks full. A launch window that opens once every 26 months, when the two planets fall into a geometry that allows a spacecraft to cross between them without spending impossible amounts of fuel, and eventually, for the horizon receding as you approach it, a fleet. 1,000 ships, a 20-year build-out, a city. The financial gravity of the project has become its own kind of number. In 2026, SpaceX reported capital expenditures of roughly $18.4 billion, an increase of over 500% on the prior year. That is not the budget of a company. That is the budget of a small nation space program, running inside the accounts of a private firm, spent almost entirely on the logistics of getting mass off this planet and eventually onto another one. Whatever else you think about the enterprise, you cannot say it is unserious. The money is real, the steel is real, the engines when they light are real, and they are the largest engines ever flown. None of that is what this documentary is about. What this documentary is about is the fact that everything in the paragraph above lives inside a single domain. Call it the engineering domain. It is the domain of thrust and mass fraction and orbital mechanics and heat shields and propellant boil-off. It is the domain in which Mars is a logistics problem, a destination at the end of a delta-V budget, a coordinate to be reached. And inside that domain, the problem, while ferociously hard, is at least legible. You can draw it on a whiteboard. You can iterate on it. You can, with enough money and enough failed prototypes, converge on a solution. The problem is that the animal you're trying to deliver to the coordinate does not live in the engineering domain. It lives in a different domain, older, wetter, more stubborn. It lives in a body that evolved over roughly 4 billion years to operate inside one specific set of conditions. A pressure, a gravity, a spectrum of light, a chemistry of soil and air and water. And when you take that body out of those conditions, it does not iterate. It fails in ways that are as measurable as any rocket equation and as unforgiving. And nothing in the current architecture, nothing in the renders, nothing in the timelines meaningfully addresses those failures. They are simply, for the purposes of the presentation, left off the whiteboard. This is not new. The generation that will be old enough to fly the first missions was raised on a specific cultural diet in which Mars figured as a solvable place. There was a novel, and then a film, in which a botanist stranded on the surface grew potatoes in his own waste and worked the problem soul by soul until he came home. NASA leaned into the film, used it as a wedge to shore up public interest in its own long-arc plans, and for a moment the gap between fiction and mission planning felt narrower than it had in decades. Before that, there was a Dutch non-profit that proposed a one-way colony, took applications from more than 200,000 people across more than 140 countries, and then, in 2019, quietly filed for bankruptcy. The applications are the interesting number. 200,000 people without any serious vetting of the plan raised their hands to leave. That is not a statistic about spaceflight. That is a statistic about the depth of the longing. The longing is real. It is worth taking seriously. It is the same longing that pushed hominids across land bridges and Polynesians across open ocean, and more recently, drove certain kinds of people north into ice and south into desert, for reasons they could not fully articulate to the people they left behind. It is not in itself an error. What is an error is confusing the longing for a plan, and confusing a plan for a mission, and confusing a mission for the survival of the specific person on the other end of it. The physicist Adam Becker, writing recently about the whole enterprise, has kept returning to a phrase, that the toxic dust of Mars is a primary and often overlooked barrier to habitation. Not the radiation, which gets the headlines, not the cold, which is obvious, the dust. The stuff that will get into every habitat, every water supply, every food chain, every lung, and cannot be washed off because there is no water to wash it with, and no atmosphere to blow it away, and no chemistry to neutralize it, that does not require another chemistry, and another after that, in a chain of dependencies that eventually terminates in Earth. He is not the only person saying this. He is one of a growing group of people, quietly, without theatrics, pointing at the parts of the render that are not there. There is also a legal register that almost never appears in the presentations. The Outer Space Treaty, which most spacefaring nations have signed, holds those nations internationally responsible for space activities carried out from their territory, whether the actor is a government or a private company. A private colony is not, under the treaty, an autonomous entity that can simply declare itself. It is a national activity for which a national government answers. That legal frame is not a fatal obstacle. It is, however, an obstacle, and it is treated in the pitches as though it were weather, something that might be there and might not, and either way will be dealt with when the ships arrive. All of this is the seduction, the renders, the timelines, the 1,000 ships, the child at the window, the child above all, because the child is the promise that this is not a mission but a beginning, and that whatever is uncomfortable about the first crossings will be paid off over generations in the ordinariness of a life lived under a rust-coloured sky. Hold on to that image for a moment. The child, the window, the second sun. We are going to come back to it at the end of this long walk and see what it looks like once we have counted honestly what it costs. For now, let us leave the renders and go to the surface. Not the imagined surface, the measured one. There are, at the time of this recording, a handful of instruments still operating on Mars, and a slightly larger handful that operated within recent memory, and left behind archives of data that constitute the most detailed portrait we have ever had of another planet's surface. Perseverance in Jezero Crater has been rolling since early 2021, and among the many things it carries is a microphone, the first microphone ever to successfully record ambient sound on Mars. Curiosity, older and further south in Gale Crater, has been taking the local weather for well over a decade, through an instrument called REMS, and until December of 2022, a lander called InSight sat in a plane called Elysium Planitia with a seismometer pressed against the ground, listening for the shudders that pass through the crust of a world. Take those three instruments and you can begin to reconstruct, in a way no artist's render will ever quite manage, what it is actually like to stand there. Start with the sound. When Perseverance's microphones came online and returned their first clean recordings, the striking thing was not the noise, it was the quiet. The Martian atmosphere is thin enough that sound simply does not carry the way it does here. Measurements suggest that ambient natural sound on Mars is on the order of 20 decibels quieter than the equivalent on Earth. 20 decibels is not a small number. It is the difference between a normal conversation and a whisper. It means that if you stood on the surface, unhelmeted, which, for reasons we will come to shortly, you would not survive doing, the world would sound to you as though someone had run it through a heavy pane of glass and then turned the volume down. The wind is there, the scrape of grit on metal is there, but everything is at a remove, muted, as if heard through a wall. There is also a stranger property of that soundscape, one that has no analogue anywhere else in the solar system that humans have visited. Because the atmosphere is composed mostly of carbon dioxide, and because carbon dioxide interacts with sound in an unusual way at low pressure, high-pitched sounds and low-pitched sounds travel at slightly different speeds. The difference is on the order of 10 meters per second. On Earth, this is not a thing that happens. A clap is a clap. The high frequencies and the low frequencies arrive at your ear together, which is why a clap sounds like a single event. On Mars, in principle, they would not. The higher components of the sound would arrive fractionally before the lower ones. Over any distance beyond a few tens of meters, a sharp impact would begin to smear into its own echo of itself, the crack arriving first, the thud arriving after. Nobody, obviously, has stood on the surface and heard this with their own ears. The instruments record it. The physics predicts it. If you were ever there, the world would sound wrong to you in a way that took a long time to articulate. And the reason would be that a fundamental property of how sound behaves in the air you grew up in had shifted very slightly into something else. Then take the temperature. Curiosity's REM station, sitting in Gale Crater at a latitude roughly equivalent to somewhere in the mid-southern hemisphere on Earth, reports numbers that at first look almost tolerable, and then, when you sit with them, do not. Daytime highs can climb to around minus 50 degrees Celsius. That is very cold. It is roughly the coldest natural surface temperature recorded on Earth, achieved on Mars as a summer noon. Nighttime lows in the same location drop toward minus 130. A single sol, a Martian day, about 40 minutes longer than ours, routinely swings through a range of 100 degrees Celsius or thereabouts. There are records in the REMS archive of shorter-term swings that are almost cartoonish. On the 3rd of September 2025, the station recorded a drop of roughly 49 degrees Celsius over just 2 sols. 49 degrees. That is the difference between a summer afternoon in Athens and a winter night in central Siberia, expressed as a change in the local weather across the span of 48 hours. Think, for a moment, about what that means for anything you might build. A material that is fine at minus 50 may crack at minus 100. A seal that holds through a warm afternoon may fail as the sun goes down. Every joint, every hinge, every window, every solar panel is going to contract and expand and contract again, on a rhythm that no engineering material on Earth has ever been asked to endure at this amplitude, this frequently for this long. It is not the average temperature that eats a habitat on Mars, it is the swing. And then there is the ground itself. InSight, before its retirement in the final days of 2022, spent about 4 Earth years listening. In that time it recorded, by the mission team's count, 1,319 Marsquakes, seismic events large enough to register on the instrument's dome. They were small, mostly. Nothing that would flatten a city. But they were persistent, and they were informative. By tracing the way the waves travelled through the interior, the seismologists were able to draw the first credible picture of what the inside of Mars actually looks like. The mantle, it turns out, is not smooth. It is studded, the papers say, with the fragments of ancient impacts, remnants of a bombardment so old that on Earth, plate tectonics erased its evidence billions of years ago. On Mars, without tectonics to churn the crust, the wounds have been preserved. You could think of the planet, if you wanted a metaphor, as a body that has kept every bruise it ever received and quietly, for 4 billion years, has been carrying them. That is Mars from the instruments. A world that is quieter than ours by 20 decibels. A world where high and low frequencies drift out of sync. A world whose weather can drop 49 degrees across 2 days, whose ground remembers every strike it has taken, whose atmosphere is so thin that the deepest place on its surface has a pressure equivalent to the top of Earth's stratosphere. This is the place the renders show as brass and warmth and windows. It is not brass. It is not warm. It is a very specific, very measurable place. And the numbers, once you start reading them, are always worse than the pictures. We have not so far come to the number that decides most of the argument. Let us come to it now. There is a threshold in the physiology of pressure that has a name attached to it. It is called the Armstrong limit, after General Harry George Armstrong, an American flight surgeon who, in the years immediately after the Second World War, founded what would become the Air Force's Department of Space Medicine. Armstrong was interested in what happened to human beings as aircraft climbed higher, and in particular he was interested in what happened when the air outside the cabin thinned to a point at which the ordinary rules of respiration no longer applied. The number he identified, the number that carries his name, is the altitude at which the atmospheric pressure drops to roughly 6.3 kilopascals, 47 millimeters of mercury. On Earth, that altitude sits at somewhere between 18 and 19 kilometers above sea level, higher than any commercial aircraft flies, higher than most weather balloons reach, higher than the summit of Everest by more than a factor of 2. The reason the number matters is that at 6.3 kilopascals, at a body temperature of 37 degrees Celsius, the temperature you and I are running at right now, the boiling point of water is 37 degrees Celsius. The two numbers meet. Below that pressure, the liquid water inside a human body wants, thermodynamically speaking, to become vapor. It is not a slow process. It is not a matter of exposure over minutes. It is a phase change, initiated the moment the pressure drops beneath the line, and it has a physiological name of its own: ebulism. Ebulism is not, contrary to a very common misconception, the boiling of blood in the arteries. The blood inside your circulatory system is contained by vessel walls that maintain a pressure of their own. It does not immediately flash. What flashes is the water that is not so contained, the saliva on the tongue, the tears on the eye, the film of moisture that lines the inside of the lungs and the sinuses and the soft palate. These fluids, exposed to a pressure below the Armstrong limit, do not simmer. They vaporize. In animal studies conducted in the 1960s under NASA support, dogs and chimpanzees exposed to pressures below 2 millimeters of mercury exhibited, within seconds, generalized muscular spasm, convulsive seizures, and visible swelling of the soft tissues of the body. The subjects survived in most cases if they were recompressed within roughly 2 minutes. Beyond that window they did not. There is a human record too from an accident. In 1965, a technician at a NASA test facility was exposed to near vacuum inside a chamber for a period of somewhere between 14 and 20 seconds before the chamber could be repressurized. He survived. He was walked out of the room and eventually made a full recovery. But he was interviewed afterward, and when asked what he remembered, he said the last thing he was aware of before losing consciousness was the sensation of his own saliva beginning to boil on his tongue. That is the Armstrong limit. That is what it means physiologically to cross it. Loss of consciousness within 9 to 12 seconds, as the oxygen dissolved in the blood exits the tissues on the wrong side of the pressure gradient. Survival possible for perhaps 80 or 90 seconds if recompression is immediate. Beyond that, the damage compounds beyond what the body can repair. Now hold the number in your mind, 6.3 kilopascals, the threshold. Below it, unprotected human tissue and open space are, for the purposes of the next 90 seconds of your life, indistinguishable. The mean surface pressure on Mars is 600 pascals, 0.6 kilopascals. It varies with season, as carbon dioxide sublimates and refreezes at the poles, oscillating between roughly 400 and 870 pascals depending on where you are and what time of year it is. At its highest, the atmosphere at the surface of Mars is roughly 1/10 of the pressure at the Armstrong limit. At its lowest, it is closer to 1/15. Say that again slowly. The best day, on the thickest part of the Martian atmosphere in the deepest basin, at the season of maximum pressure, is still an order of magnitude below the threshold at which the water in your soft tissues wants to become vapor. There is no altitude on Mars, no crater floor, no canyon bottom, at which you could stand unhelmeted for 10 seconds and expect to walk away. Let me put that in perspective in one more way, because it is the load-bearing number of everything that follows. If you took the densest air anywhere on the Martian surface and compared it to the air here on Earth, you would have to climb to roughly 35 kilometers, twice the altitude of the Armstrong limit, more than 3 times the cruising altitude of a passenger jet, before you found Earth air as thin as Martian air at its thickest. The peak of Everest, at 9 kilometers, has more than 100 times the pressure of the Martian surface. The stratospheric balloons that carry scientific instruments to the edge of space float in an environment that is, by pressure, essentially Martian. This is not an atmosphere in the sense that the word usually implies. It is a trace. It carries sound, barely. It carries dust, which is the only reason there is weather to speak of at all. It does not carry oxygen worth mentioning. It does not carry pressure sufficient to keep the water in a human body in the liquid state. Physiologically, the Martian surface is not thin air. Physiologically, the Martian surface is space, with a small amount of debris blowing across it. Every habitat, every suit, every airlock, every window on every render is a wall between a body that evolved at 101 kilopascals and a world that averages 600 pascals. That wall is not a comfort. It is the entire margin. If it fails, if a seal degrades, if a valve sticks open, if a piece of dust that we'll meet properly in a later chapter works its way into a gasket and prevents it from closing, the person on the wrong side of the failure has, at best, about 90 seconds before recompression stops being useful. That is the pressure line. That is where blood, in the loose everyday sense of the word, meets vacuum. It is the first of the incompatibilities we have to walk through, and in some ways the cleanest, because it is not a matter of long-term degradation or slow accumulating risk. It is immediate. It is binary. It is the wall or the wall's failure, and there is nothing between the two. Rest with that for a moment. Say the number to yourself, 600 pascals, 1/100th of the Armstrong limit, and then hold the child at the window in your mind and ask yourself what is actually on the other side of the glass she is pressing her hand against. We're only at the beginning. There is another wall, and it is stranger than the first because it is not a wall you can see. It is inside the soil. It is inside the dust that drifts across the soil. It is inside the thin skin of frost that forms on the shaded side of a rock at dawn. And it is inside the fingerprint of grit that the wind will press onto the outside of every camera lens, every solar panel, every helmet visor, every glove, every airlock seal, every threshold that a human being will ever try to cross on that world. The wall between the body and the vacuum is a wall you build. The wall we are about to walk into is a wall the planet has already built, and it does not care whether you know it is there. The date, if you want a date, is the 25th of June 2008. The place is a landing site in the northern plains of Mars, a broad, flat sweep of terrain called Vastitas Borealis, chosen because underneath a few centimeters of dust and grit there was, unambiguously, water ice. The lander was called Phoenix, and it had been designed more or less to scoop that ice, warm it, sniff it, taste it, and tell us what was in it. It had a small oven for baking soil samples, it had a robotic arm that could dig a trench the size of a shoebox, and it had, tucked into the deck, a set of 4 small cups called the Wet Chemistry Laboratory, each about the size of a teacup, each capable of receiving a scoop of Martian soil, mixing it with a measured volume of water brought from Earth, and reading, with a set of electrodes, what dissolved out of the dirt. The principal investigator of that mission was a man named Peter Smith from the University of Arizona. He is on record, and the phrase has been repeated so often since that it has taken on a kind of dry, exhausted humour, saying that when the first set of results came back from the wet chemistry laboratory, none of the scientists in the room could immediately say what they were looking at. Perchlorate, he said, is not a common word in the English language. All of us had to go and look it up. They looked it up, and then they went back to the data, and then they ran the experiment again on a fresh sample of soil, and then they ran it a third time, and the answer would not go away. Perchlorate, in the Martian dirt, not a trace, not a whisper at the edge of the instrument's sensitivity. A frank chemical shout. Between 0.5% and a full percent of the soil, by mass, was a family of oxidized chlorine salts, of which the most abundant and the most familiar to industrial chemistry was perchlorate. And that number, in the context of Earth, is difficult to convey without stopping to consider what the equivalent number would look like on the planet you're standing on now. On Earth, perchlorate is a regulated contaminant. It shows up around old rocket fuel test sites, around fireworks factories, in the groundwater near certain military bases, and it is regulated in drinking water at concentrations measured in single-digit parts per billion. 18 parts per billion, at some of the stricter thresholds. Below that, the water is considered safe. Above that, remediation is required. A percent by mass, which is what Phoenix found in the soil at Vastitas Borealis, is 10,000 parts per million. 10 million parts per billion. Not 18. 10 million. Say that once more, slowly. The Martian soil, in the first place a spacecraft ever dug into it looking for water, contained perchlorate at a concentration roughly 500,000 times the level at which Earth regulators tell us not to drink the water. The obvious question, and it was the question everyone on the science team asked in the following weeks, was whether this was a fluke. Vastitas Borealis is one small patch of one hemisphere of a whole planet. Phoenix had scooped, in the end, from a handful of trenches in an area you could walk across in a lunch break. Perhaps this was contamination local to the ice-rich northern plains. Perhaps some quirk of that latitude, that soil chemistry, that history of frost and thaw had concentrated an otherwise rare compound in one spot, and the rest of Mars was clean. It was not a fluke. The confirmation came 4 years later, and it came from the other side of the planet. In 2012, the Curiosity rover set down in Gale Crater near the equator, in a landscape geologically and geographically about as different from Vastitas Borealis as two Martian sites can be. In its belly, Curiosity carried an instrument called SAM, the Sample Analysis at Mars Suite, a compact chemistry laboratory that could bake a soil sample, sniff the gases that came off, and identify the compounds present at parts per billion sensitivities. SAM baked its first samples, and the volatiles that boiled off carried the unmistakable signature of oxychlorine compounds, perchlorates, chlorates. The same family Phoenix had found on the other side of the world, two spacecraft thousands of kilometers apart, landing in unrelated terrain, digging into unrelated soil, and finding the same chemistry. That is not a local contamination. That is a planetary property. And when the orbital datasets were reviewed with fresh eyes, the picture became harder to argue with. The Mars Odyssey orbiter, from a great height, had already mapped the distribution of chlorine across the entire surface of Mars, using the faint gamma-ray signature that chlorine emits under cosmic ray bombardment. That map showed chlorine everywhere. Not uniformly, not identically, but everywhere. There was no clean hemisphere, there was no perchlorate-free continent. Wherever the wind blows, the dust carries the salt. There is even, reaching backwards, an old ghost in this story. In 1976, the two Viking landers ran a suite of experiments looking for signs of life in the Martian soil, and among the things they did was heat a soil sample and look for the organic molecules that might come off it. What they found when they ran the analysis were small chlorinated hydrocarbons, compounds that at the time were largely dismissed as contamination from cleaning fluids used on the spacecraft before launch. Looking at those results now, with what we know from Phoenix and Curiosity, the picture rearranges itself. The Vikings were not measuring their own cleaning fluid, they were measuring what happens when you take Martian soil, which is soaked in perchlorate, and heat it in the presence of any organic molecule at all. The perchlorate is a strong oxidizer at temperature. It attacks the organics, It produces chlorinated hydrocarbons. The Vikings had already, in 1976, brushed against this chemistry. Nobody knew what they were looking at. Peter Smith's team had to look up the word. Now step back from the history of the discovery and consider what perchlorate actually does inside a human body. The molecule is small. It is chemically similar, in the eyes of one particular protein in your thyroid gland, to iodide, which is the ion your thyroid needs to build the hormones that regulate your metabolism, your temperature, your growth, your neurological development. The protein is called the sodium iodide symporter, and its job is to pull iodide out of your bloodstream and into your thyroid cells so it can be built into hormone. Perchlorate chemically fits into the same door. It sits in the symporter. It does not get built into anything. It simply occupies the space that iodide should have occupied, and while it is there, no iodide gets through. The consequence at chronic low doses is a slow starvation of the thyroid. Hormone production drops. The condition is called hypothyroidism, and its symptoms are the ones people associate with a body running at low idle. Fatigue, cold intolerance, weight gain, cognitive fog, depression, slowed reflexes, and eventually, if uncorrected, more serious cardiovascular and metabolic complications. In an adult, the condition is manageable with iodine supplementation, and if necessary with synthetic thyroid hormone, and life continues. It is not, in an adult, a death sentence. It is a chronic burden. In a developing body, it is a very different matter. Fetal and infant brain development depends on thyroid hormone at specific stages. If those stages arrive and the hormone is absent or reduced, the consequences are not reversible. Structural abnormalities in the brain, learning impairments, cognitive deficits that do not fade. This is not speculation. This is the well-established terrestrial pharmacology of a compound that has been studied for decades in the context of rocket fuel groundwater contamination and thyroid medicine. It is the reason perchlorate is regulated in drinking water in parts per billion, not parts per million. And now put that pharmacology into the context of a Martian habitat. Every scoop of regolith brought inside for any purpose, to extract water, to test for construction feasibility, to grow a plant in, carries perchlorate. Every crevice in every glove, every fold in every fabric, every seam in every boot brought back through the airlock carries perchlorate. Every filter in every life support system that ever catches a stray dust grain from an EVA carries perchlorate. Water extracted from the Martian ice caps, unless meticulously purified, carries perchlorate because the ice and the soil have been in contact for billions of years, and perchlorate is deliquescent. It pulls water out of the environment and dissolves into it, and the salts have leached into every ice deposit that ever thawed and refroze. This is not a hazard that a mission can contain by staying tidy. This is a hazard that lives in the medium the mission is walking on, breathing near, drinking from, and eventually, if the vision holds, farming in. And any calculation about the safety of children born on Mars, the children in the rendered windows watching the sunset, has to reckon with the fact that unless the perchlorate is stripped, at every stage of every input, from every scoop of soil that ever touches a human system, there is a non-trivial baseline dose of a known endocrine disruptor sitting quietly in the environment of gestation. Nobody knows exactly what the threshold is, in a partial gravity environment, in a body already under other stresses. Nobody has run that experiment. Nobody can. What we have is the terrestrial pharmacology and the Martian chemistry, and the two do not fit together comfortably. Let that settle. The soil is poisoned, not in the sense that a spill has poisoned it, or a factory has poisoned it, or a war has poisoned it, in the sense that this is what the soil is. The oxidation of chlorine on that surface, over billions of years, under a thin atmosphere flooded with ultraviolet light, has produced a planet-wide layer of a compound that our biology treats as an imposter for a nutrient we cannot live without. There is nothing malevolent in it. There is nothing to be angry at. The planet was not made for us, and the chemistry that shaped it did not consult our endocrine glands. Now, let us turn to the dust, because the dust is the delivery system, and the dust is where the story becomes not just chemical but mechanical, not just something in the ground but something in the air, something in the eyes, something in the lungs, something that gets everywhere and cannot be persuaded to leave. Consider the size of the particles first. Martian dust averages 1 to 3 micrometers across. Some grains reach 20 micrometers, but the bulk of what hangs in the air, what settles on surfaces, what infiltrates seams and gaskets and any gap wider than a hair, is in that 1 to 3 micron range. To give that a scale a human body understands, the finest cosmetic powder you have ever touched, the baby powder that leaves a residue on your fingertips for hours after you have washed your hands, is roughly 5 to 10 times coarser than Martian dust. If you have ever tried to keep flour off a countertop, or plaster dust out of a room, or wildfire ash off a car parked in a driveway 100 miles from the fire, you already know what the losing side of that fight feels like. Martian dust is finer than any of those, and unlike any of those, it is electrostatically charged. The charge is not an incidental property. It is generated continuously, by friction, in every dust devil that skitters across the plains, in every global storm that lifts curtains of the stuff into the sky for weeks at a time, in every gust that scrapes one grain against another. The friction knocks electrons loose, the grains become polarized, and once polarized, they cling. They cling to metal, to glass, to fabric, to the transparent visor of a helmet, to the surface of a solar panel, to the sensitive optics of a scientific instrument, with a stubbornness that is difficult to overstate. Wiping does not remove them. Brushing embeds them further. Compressed gas can dislodge some fraction of them, but the rest are held by an attraction that treats human effort as an inconvenience. We already know what this does to a machine, because we have watched it happen. The Spirit rover, one of the 2 Mars exploration rovers that landed in 2004, ran for years on solar panels that its designers hoped would occasionally be cleaned by wind. Sometimes, unexpectedly, they were. A gust would come through, lift some fraction of the accumulated dust, and the rover's power budget would recover. It was one of the small, wonderful surprises of that mission. But in 2008, a major dust storm settled over the Gusev crater region, and the panels darkened, and the power dropped from the healthy levels the rover had been running at down through the margins, down toward the floor at which the rover could no longer keep itself warm through the Martian night. Spirit fought on reduced rations for another year and a half. But the fundamental problem never lifted. The dust came, and the dust stayed, and the dust that stayed made every subsequent problem worse. The mission ended in the end, because the machine could not see the sun through the coat of grit the planet settled onto it. The engineers who designed Perseverance took that lesson seriously. Perseverance carries a small tool called the gaseous dust removal tool, which fires short, sharp puffs of nitrogen at surfaces that need to be clean. The abraded patches on rocks that other instruments need to examine, the sensitive covers over other detectors. It works, imperfectly. Even with the tool, dust has crept in around the edges of instruments. There have been small failures of dust covers that were supposed to open cleanly, and did not, held by grit in mechanisms that were designed with tolerances tighter than the grit likes to allow. This is on a rover designed by people whose entire professional lives are spent thinking about how to keep dust out of things. If a nuclear-powered laboratory the size of a car, built by NASA's best, is still losing small skirmishes to Martian dust, one does not have to strain the imagination to see what happens to a habitat full of soft goods, elastomer seals, filters, and human beings. And now, put the two facts together. Martian dust is 1 to 3 microns across, electrostatically charged, capable of infiltrating any seal that is not truly hermetic. Martian dust is chemically identical to Martian soil, which is to say between 0.5% and 1% perchlorate by mass, plus a witch's brew of iron, oxides, silicates, and other oxidizing chemistry that ultraviolet light and cosmic rays have activated at the surface. Every EVA suit that touches that surface, and every suit that touches that surface is every suit, because there is no way to walk on Mars without touching Mars, is coated, on its return to the airlock, in a fine electrostatic layer of the salt. The dust does not fall off. The dust does not brush off. The dust rides the suit back through the airlock like a passenger, and once inside the pressurized volume, the same low gravity that lets it hang in the Martian sky for months, lets it hang in the habitat air for hours, drifting, settling on surfaces, being disturbed again the next time someone walks past. There is a scenario, endlessly redrawn in the concept art of Martian habitation, called a suit port, in which the suits live permanently outside the habitat attached to the exterior wall, and the astronaut enters and exits by climbing through a hatch in the back of the suit from inside. The dirty outside stays outside, the clean inside stays clean. It is an elegant idea, and every serious human Mars study takes it seriously, and every serious human Mars study also acknowledges that it does not solve the problem completely, because samples still have to come inside, and instruments still have to be serviced, and eventually the seals on the suit ports themselves will have to be inspected, and the dust, which does not care about elegant design, will find the gaps that elegance did not anticipate. The inhalation risk if the dust does reach a habitat's atmosphere is the last piece of this. Particles between 1 and 3 microns are precisely the size range that penetrates deepest into human lungs. Larger particles are trapped in the upper airways and coughed out. Smaller particles are exhaled again on the return breath. The 1 to 3 micron range is the range that reaches the alveoli, the deep gas exchange sacs at the bottom of the lung, and stays there. Terrestrial equivalents are silicosis, in miners who breathed rock dust, and black lung, in miners who breathed coal dust. Diseases in which the lungs, over years and decades, harden and scar in response to particles the body cannot expel. Martian dust, size-wise, is in that regime. Whether it produces the same pathology, we do not know. Whether the perchlorate coating adds an oxidative burden on top of the mechanical one, we do not know. Nobody has run the experiment. Nobody can. What we have is the geometry of the particles, the chemistry of their surfaces, and the terrestrial history of what happens to lungs that meet particles of the wrong size for too long. Regulatory bodies are aware of this. There are working groups actively trying to write a permissible exposure limit for Martian dust in a habitat atmosphere, a number in micrograms per cubic meter, below which the risk to accrue over a mission is considered acceptable. There is no such number yet. The dust we have measured is not the dust anyone has breathed. The dust anyone has breathed is lunar dust, which is different in size and chemistry, and terrestrial analogues, which are different in nearly every way. The Martian number is being written into a blank space in the regulations, and it is being written in the honest knowledge that we are guessing. Rest with that for a moment. The soil is a low-grade chronic poison. The dust is a fine, charged, uncleanable carrier of that poison. The two are the same substance. Everything you touch on Mars, if you are not extraordinarily careful, becomes a way of bringing the outside in, and the outside, chemically, is not neutral. We have not yet said anything about what falls on that same surface, unattenuated day after day from the sky. We have not yet said anything about the particles that arrive not on the wind but from the galaxy, at a fraction of the speed of light, passing through spacecraft hulls and habitat walls and human tissue as if none of it were quite there. The pressure line is one wall, the dust is a second. The third begins before the ship even reaches the planet. The instrument that first told us how much of it there was is called the Radiation Assessment Detector, or RAD. It is a small, dense instrument built jointly by the Southwest Research Institute in Colorado and Christian Albrechts University in the German city of Kiel, and it flew to Mars in the belly of the Mars Science Laboratory, the spacecraft that carried the Curiosity rover, during the 8-month cruise between Earth and Mars in the winter and spring of 2011 and 2012. The scientists most closely associated with it are Don Hassler, the principal investigator, and Carrie Zeitlin, the lead author on the paper that would, in May of 2013, publish in the journal Science what RAD had measured on the way over. RAD was, in a sense, doing something the space age had not done before. Every previous measurement of interplanetary radiation had come from instruments mounted on the outside of a spacecraft, or on a small probe with minimal shielding, or on the surface of the Moon, which is inside Earth's magnetic sphere of influence for a significant fraction of every orbit. RAD was sitting inside the hull of a Mars-bound craft, at the back of a stack of shielding roughly equivalent to what a crewed vessel might carry, measuring what actually reached the interior. Measuring, in other words, what a human being tucked into that same interior would have received. The number that came back, and that Zeitlin and his colleagues published, was approximately 300 millisieverts, for a one-way transit of about 180 days. That is the dose equivalent, the biologically weighted measure that accounts for the different damaging power of different kinds of radiation, accumulated by an instrument sitting where a person's body would sit over the course of a cruise from Earth to Mars. 300 millisieverts. Say that number slowly, because it is one of those figures that sits inertly on the page and only comes alive when it is put next to something a human being can feel. On Earth, a person going about an ordinary life, living in a house, eating ordinary food, occasionally boarding an airliner, occasionally having a chest X-ray. accumulates something on the order of 3 millisieverts a year from all sources combined. 300 millisieverts is 100 years of ordinary living delivered in 6 months. It is roughly 15 times what a nuclear power plant worker in most jurisdictions is permitted to receive in a year of professional exposure, and those workers are considered a specially monitored occupational class, tracked with dosimeters clipped to their coveralls and pulled off the floor if their annual number climbs too high. Rad's cruise dose was that permitted number times 15, delivered whether the passenger wanted it or not, with no shielding option beyond the aluminium already wrapped around them, and no way to step outside the exposure until the ship arrived. And that was only the trip over. The instrument kept measuring after it landed. Curiosity touched down in Gale Crater in August of 2012, and Rad, still tucked inside the rover, began sampling the radiation environment at the Martian surface, the environment a standing human would inhabit, minus the small attenuation of a rover's chassis. The number that stabilized, averaged over the long run of Martian days, has been reported at roughly 0.64 millisieverts per day. Some intervals run a touch higher, some a touch lower, depending on solar conditions and the seasonal thickness of the atmosphere overhead. But 0.64 is the figure the community has settled around, and it is the figure to hold in mind. 0.64 millisieverts a day does not sound like much. Fractional numbers rarely do. Multiply out and it opens. A Martian year is not the number to use because the mission is not clocked in Martian years. Use Earth days. 365 of them, at 0.64 each, comes to roughly 230 millisieverts of dose equivalent, absorbed by a person doing nothing more strenuous than existing on the surface of the planet for one Earth year. 230 millisieverts. Roughly 75 years of ordinary terrestrial background, compressed into 12 months. Roughly 10 times the annual limit for the nuclear worker in her lead-lined room. Absorbed by breathing, by sleeping, by walking across the habitat floor. Absorbed at rest, absorbed in exercise, absorbed while eating a meal. There is no posture on the surface of Mars that turns the dial down. Now take the mission architecture that most agencies quietly assume for a first serious human expedition, and lay it against those numbers. The nominal shape is roughly this: 180 days of outbound cruise, during which RAD-class instruments have measured something closer to 1.8 millisieverts per day inside the ship, higher than the surface rate, because deep space is a harsher environment than a planet that at least has a floor beneath its sky. Then 500 days on the surface, waiting for the orbital geometry between Earth and Mars to align again for a return window. Then another 180 days of cruise home. Do the arithmetic slowly. 180 days of transit at roughly 1.8 millisieverts per day is on the order of 324 millisieverts, one way. Doubled for the return, 648. 500 days on the surface at 0.64 is another 320 millisieverts. Add them together, and the honest total for a single nominal mission lands somewhere in the vicinity of 1 sievert. Perhaps a little less, perhaps a little more. The dosimetric community tends to quote figures between 1.01 and 1.1 sieverts for this profile. Say 1 sievert and hold it, 1 sievert. Here is where the number stops being an accountancy exercise and starts being a medical one. The National Academies of Sciences, Engineering and Medicine periodically convene a committee to synthesize everything the scientific community knows about the biological effects of low-level ionizing radiation, and to publish the result as a report. The most influential of these is called the Biological Effects of Ionizing Radiation Report, Phase 2, Beer 7 in the shorthand, and its central conclusion, arrived at by extensive review of atomic bomb survivor data, occupational exposure data, medical exposure data, and everything else the field has learned in 8 decades of study, is that there is no threshold below which radiation exposure carries zero cancer risk. The relationship, so far as anyone can tell, is linear. Halve the dose, halve the risk. Double the dose, double the risk, all the way down. Under the Beer 7 models, a cumulative dose in the vicinity of 1 sievert is associated with something on the order of a 5% increase in the lifetime probability of developing a fatal cancer. Not 5% chance of dying of cancer, in absolute terms. That baseline sits already at roughly 1 in 5 for a person living out an ordinary lifespan, but 5 percentage points added on top of that baseline, attributable directly to the mission. 1 astronaut in 20, on this arithmetic, would eventually die of a cancer they would not otherwise have developed, because they went to Mars and came back. Let that settle, not as a headline, as a fact of employment. Every crew member volunteers in signing the papers to accept a risk of that shape, and every crew member does so on the basis of a model, the linear no-threshold model, that scientists themselves regard as the best available guess, not as gospel. The honest answer is that we do not know exactly what one sievert of galactic cosmic ray exposure does to a human body over the decades that follow. There has never been a cohort of human beings who received it in this way, at these energies, in this composition of particles, and lived long enough afterwards to be tracked to the end. The 5% is a projection. The reality might be gentler. The reality might be harsher. The people who sit down with the actuarial tables will tell you quietly that the uncertainty bars on that number are wider than the number itself. And here is the piece that no engineering fix erases. The particles that make up most of that dose are not the low-energy particles you can stop with a modest thickness of metal or plastic. Galactic cosmic rays are, on average, the nuclei of atoms accelerated to a substantial fraction of the speed of light by processes elsewhere in the galaxy. Supernovae, the shocks around active stars, mechanisms astronomers are still refining their understanding of. When one of them enters a shielded volume, it does not politely stop at the outer wall. It smashes into the atoms of the wall itself and produces a spray of secondary particles, neutrons, protons, lighter fragments, that continue on into the interior. Add too little shielding, and you get the primary particle plus its secondaries. Add a lot of shielding, and the primary is more likely to be stopped, but the secondaries multiply. There is a middle range where the total dose actually increases with added mass, before it begins to decrease again. Shielding a Mars ship is not a matter of piling on more aluminium. The physics fights you. Mars itself, once you get there, offers only partial help. The atmosphere is thin, roughly 1% of Earth's, at surface pressure, and while that thin veil does absorb some of the incoming flux, it is not remotely equivalent to the 10 meters of water-equivalent shielding that Earth's atmosphere provides at sea level. The planet has no global magnetic field. 4 billion years ago it had one. The fossil traces are still visible in the ancient crust of the southern highlands, magnetized bands where a dynamo once operated in a molten core. That dynamo shut down. The core cooled, or stopped convecting, or lost whatever combination of temperature and rotation kept it stirring, and the field went away. What remains is a sky through which cosmic rays travel unimpeded to the surface, and once they strike the regolith, the loose, iron-rich dust and rock that covers everything, they generate a second population of particles, called albedo neutrons, that scatter back upward into the environment. Roughly a fifth of the surface dose, on some accountings, comes from this upward flux, from the ground itself, activated by the rain from above. There is no natural shelter above ground. That sentence is worth saying twice. There is no natural shelter above ground. Not a cave overhang, not a stand of trees, not a body of water, not a cloud layer thick enough to filter the sky. On Mars, everything you can see with your eyes from a standing height is exposed. The habitat modules of any plausible first mission will have walls of centimeters, not meters, and their occupants will absorb their 0.64 millisieverts a day, whether they are asleep or awake, whether they are working or reading, whether they are aware of it or not. And this is only the constant background. Above the steady drizzle of galactic cosmic rays sit the occasional, unpredictable events called solar particle events, the flares and coronal mass ejections that the Sun periodically hurls into the space around it. Most miss Mars entirely. Some sweep across the planet in transit. When one does, the surface radiation environment can rise over hours or days to levels that in the worst historically recorded cases would carry acute risk. Not merely elevated lifetime cancer probability, but symptoms of radiation sickness in the near term. Every serious mission architecture assumes, therefore, a dedicated storm shelter, a small volume, usually buried under a piled-up berm of Martian soil or wrapped in the ship's water tanks, into which the crew retreats for the duration of the event. The rest of the time, they live in the thinner shielding of the habitat proper and accept the constant background. The RAD team, in their published papers, describe the Martian environment with an economy of language characteristic of scientists who prefer their nouns to do the emotional work. The environment, they write, is highly radioactive and complex. That is the sentence. Highly radioactive and complex, everything a colony designer has to solve for is packed into those 4 words. There is no natural surface-level protection, and the only remaining route to something like terrestrial safety runs through deep tunneling, or through meters of piled regolith, or through habitats sunk below the ground line and roofed with mass. We will come to those solutions. They exist on paper, and some of them are quite elegant. But they are what human ingenuity has to do to compensate for the fact that the sky, on the surface of Mars, is a slow radiological wound. The body absorbing that wound is also at the same time unloading. This is the second slow erasure, and it is one we understand better than the first, because we have watched it happen to more than 100 human beings. On the International Space Station, at an altitude of about 400 kilometers, astronauts live in something very close to true weightlessness. Not quite zero gravity in the strict sense. Earth's pull is still nearly as strong up there as it is on the ground. But the station and everything in it are in continuous free fall around the planet, and the felt effect on a human body is indistinguishable from having no weight at all. In that environment, the human skeleton behaves in a way that surprised no physiologist, but startled almost everyone else. It begins to dissolve. The numbers are astonishingly consistent across missions and across bodies. Bone mineral density, in the weight-bearing bones of the hips, the pelvis, the lower spine, declines by roughly 1 to 2% per month of exposure to weightlessness. Say that at the low end, 1% per month. In a single month in orbit, a healthy adult astronaut in her 30s loses about as much bone density as a postmenopausal woman on Earth loses in a full year of ordinary aging. That is the baseline rate. Some individuals lose faster, some lose slower. Nobody, on any measured mission of significant duration, has held steady. The loss is not evenly distributed through the skeleton. Bones that do not bear weight on Earth, the arms, the skull, the ribs, are largely spared, because they were never being asked to hold anything up in the first place. Bones that carry the body against gravity, the femur, the tibia, the vertebrae of the lower back, the pelvis, are the ones that give up their mineral content because the body, in its slow economy, has decided that a scaffold that is not being loaded is a scaffold it does not need to maintain at full strength. The calcium leaves the bone, it enters the bloodstream, it filters through the kidneys, and there, in one of the small mean secondary effects of the same process, it concentrates, along with other stone-forming minerals, into a chemistry that dramatically raises the risk of kidney stones during and after the mission. A calcium balance that on Earth sits roughly at 0, in weightlessness runs at something on the order of minus 250 milligrams per day. The astronaut is, quite literally, urinating out her skeleton, and some of what she is urinating out is trying to crystallize on the way. The muscles unload alongside the bones and faster. In the first week or two of weightlessness, the anti-gravity muscles, the ones that on Earth spend the day resisting the pull of the planet, the quadriceps that hold you standing, the muscles of the trunk that keep you upright in a chair, begin to atrophy at rates that surprised the early flight surgeons, roughly 1% per day in some measurements of certain muscle groups in that first fortnight. The rate slows as the body reaches a new, lower equilibrium, but it does not stop, and the equilibrium the body finds is not the equilibrium a person needs in order to walk normally on a planetary surface when they get out. The heart itself, being a muscle asked to work against a smaller effective load, thins and rounds. Cardiac mass declines. Stroke volume declines. The cardiovascular reserve that lets an ordinary person climb a flight of stairs without thinking about it erodes, slowly, over months, into a reserve that is not always adequate. Then there are the eyes. Beginning around 2011, NASA physicians began describing a syndrome they initially called Visual Impairment Intracranial Pressure Syndrome, or VIP, and later renamed, in a more careful phrasing, Spaceflight-Associated Neuroocular Syndrome. Astronauts who had spent long durations in weightlessness were returning with changes in the shape of the back of the eye, flattening of the posterior globe, folds in the choroid and retina, swelling of the optic disc, and in some cases with lasting shifts in their vision that required new prescriptions and, more worryingly, hinted at pressures inside the skull that were not fully understood. The best current hypothesis involves the redistribution of fluids in the body once gravity is removed. The plasma and lymph that on Earth pull downward toward the feet migrate upward in weightlessness, and the pressures inside the head, including quite possibly the pressure of cerebrospinal fluid on the back of the eyeball, shift accordingly. It is a subtle process. It is also, if the mission is long enough, a permanent one. Scott Kelly is the name most often attached to this literature, because Kelly spent 340 days aboard the station, a mission specifically designed from the outset as a longitudinal medical experiment. He returned to Earth in March of 2016 measurably taller than when he had left, because the discs of his spine, no longer compressed by his own weight, had spent nearly a year expanding by up to 3% of body height across the astronaut core as a whole. He returned with his eyes changed. He returned with his bones lighter, his muscles smaller, his cardiovascular capacity narrower, and with a period of rehabilitation ahead of him that lasted, in various forms, for years. Twin studies with his brother Mark on the ground provided for the first time a genetically matched control against which to read the physiological cost. To fight all of this, the crew aboard the station exercises. They exercise a great deal. The rough figure is around 2.5 hours per day of resistive and aerobic work, 6 days a week, a regime more punishing than most Olympic training programs, embedded into a working life on which other tasks are still expected, using specialized machines that simulate loading against elastic resistance or vacuum-driven pistons, because a conventional barbell in weightlessness weighs nothing. And even with that regime, the loss is only slowed. It is not stopped. The bones still lighten, the muscles still shrink, the heart still thins. Exercise is a countermeasure, not a cure, and returning astronauts still land as physiologically compromised passengers who require assistance out of the capsule. And after they land, a follow-up study of 94 astronauts drawn from the lifetime surveillance of astronaut health database reported something that put another quiet weight on the whole architecture. 1 year after returning to Earth, only about a third of astronauts had recovered their pre-flight bone mineral density at the hip. About 47% had recovered at the spine. The rest carried a durable deficit, perhaps for the remainder of their lives, from a mission measured in months. The bones do not always come back. This is the data set we have. It is the closest available proxy to what a human body will do on Mars, and it is a proxy with an enormous, honest asterisk on it, because Mars is not zero gravity. Mars is 0.38 g. The surface pull on Mars is about 38% of Earth's. A woman who weighs 70 kilograms at home would weigh about 26 on the plains of Utopia, and nobody, in the entire history of spaceflight, has ever lived in that intermediate condition long enough to find out what it does. Every measurement we have of bone loss, muscle atrophy, cardiac remodeling, and ocular change comes from the extreme case, full weightlessness, or a passing minute of it. The interior of the curve is a blank. There is a hypothesis, held with varying degrees of confidence across the field, that some fraction of Earth's gravity is enough, that there is a crossover somewhere between 0 and 1 g, above which the body loads its skeleton adequately, maintains its muscles, keeps its cardiovascular tone, and stabilizes the pressures in the head. Where that crossover sits, nobody knows. It might sit at 0.7 of Earth's gravity. It might sit at 0.5. It might sit above 0.38, which would mean that a permanent Martian settler is on a slower version of the ISS curve, still losing bone, still losing muscle, still deconditioning, only more gradually. There is one recent piece of evidence that gestures uncomfortably in that direction. A 2026 study in Science Advances, using a small centrifuge platform aboard the International Space Station to raise laboratory mice through a range of partial gravity conditions, reported that skeletal muscle atrophy was mitigated at about 2/3 of Earth's gravity, but not at levels closer to Martian. It is a mouse study, and mice are not people, and the platform was small and the exposure was short. It is a hint, not a verdict. But it is the direction the hint points in, and no honest reading of it lets you conclude that 0.38 g is enough. We do not know. That is the sentence. We do not know whether Martian gravity will hold a human body together indefinitely, or whether it will simply slow the same erasure to a subtler, longer arc. We do not know whether the first generation of children born on Mars, if that ever happens, will grow into skeletons that can stand upright on Earth, or whether they will be, functionally, a population that cannot come home. We do not know the crossover point. We have never measured it, and the only way to measure it in the end is to send people to live in it for years and to watch what happens to them. Which brings us to the third slow wound, the one that is not chemical and not radiological, but which sits in the space between the ears of every person who goes. In the summer of 2010, in a purpose-built facility in a Moscow research campus belonging to the Institute of Biomedical Problems, 6 men climbed through a hatch into a set of hermetically sealed modules amounting to roughly 550 cubic meters of habitable volume, and the hatch was closed behind them. They did not open it again for 520 days. The project was called Mars 500, and it was, at that point, the most ambitious ground-based simulation of a Martian mission that anyone had attempted. The crew was 3 Russians, the commander Alexei Sitev, the surgeon Sukrob Kamolov, the physiologist Alexander Smolevsky, 1 Frenchman, the engineer Romain Charles, 1 Italian, the engineer Diego Urbina, and 1 Chinese citizen, Yue Wang. They lived together in a set of 4 interconnected modules meant to simulate an interplanetary spacecraft, with an additional module attached to represent the Martian surface, into which a subset of the crew notionally descended in suits at the appointed point in the mission arc. All their communications with the outside world, with mission control, with their families, with anyone at all, were subjected to an artificial delay that grew as their simulated distance from Earth grew, and that peaked at 20 minutes each way in the depths of the pretended cruise. A message home at the far end of the mission would take 20 minutes to arrive. Any reply would take another 20. A question and its answer, 40 minutes apart. There was no real-time conversation with Earth for months at a stretch. They were not, of course, actually in space. They knew this. Everyone knew this. If a genuine emergency had arisen, a fire, a medical crisis, a psychological break, the outer hatch could have been opened in minutes, and they could have walked out into the Moscow air. The knowledge of that escape route was itself a factor the researchers accounted for, and even with that knowledge, even with the reassurance at some level that a Moscow parking lot lay on the other side of the metal, the mission produced findings that reshaped the way flight surgeons think about the psychology of a real Mars crew. 4 of the 6 men developed significant sleep disturbances during the mission. Their circadian rhythms, unmoored from a natural day-night cycle, began to drift. Some began to nap in the day and lie awake at night. Sleep quality declined across the crew, and with it went cognitive sharpness. Reaction times slowed, small errors accumulated. The fine grain of attention that a real mission would demand began to fray at its edges. As the months wore on, the researchers watching from outside noted a phenomenon they described cautiously as a kind of behavioural torpor. The men moved less, rested more, conserved themselves. They were not depressed in the clinical sense. They were withdrawn. Their world had shrunk to a set of walls, and their bodies had adjusted to the smallness of it. Interpersonal stress emerged, as it always does in confined groups, and it emerged along predictable lines. 2 of the 6 crew members, the 2 who reported the highest personal stress and the greatest physical exhaustion, were, between them, involved in roughly 85% of the perceived interpersonal conflicts across the mission. The rest of the crew, in effect, learned to navigate around those 2, and to hold the group together by absorbing what would otherwise have fractured it. The dynamic is one that anyone who has lived in a small team under pressure will recognize. The observation was that even in a carefully selected, extensively screened, professionally trained group of 6, the arithmetic of conflict concentrated. They passed through what the psychological literature calls the 3rd quarter phenomenon, a pattern observed in Antarctic winterovers and submarine crews and other long isolations, in which mood and motivation dip most sharply not at the beginning of a confinement, nor at the end, but in its 3rd quarter, when the novelty is long gone and the exit still lies far away. They developed over time a strange bias in their emotional responses to imagery, a tendency to rate unpleasant pictures more positively than they had rated them at the mission's start, which the researchers interpreted tentatively as a psychological defense, a way for the mind to reduce the emotional weight of a monotonous environment by dampening its own capacity to be disturbed. And then, on the 4th of November 2011, 520 days after they had entered, the 6 men opened a hatch onto a paved surface in a Moscow suburb, blinked in the November light, and walked out into a crowd of researchers and family members and cameras. They had, in every measurable sense, come home, but the home they had come to was one they had never truly left. Now imagine that same envelope stretched to a real mission. The delay is not artificial. The delay is imposed by the speed of light and the geometry of 2 planets on their orbits, and at the far point of a real Mars mission, it climbs beyond 20 minutes each way toward peaks past 22. There is no researcher outside the hatch. There is no hatch in any meaningful sense. The outer door opens onto a surface that will kill an unprotected human in seconds. There is no evacuation. There is no medevac. If a crew member develops appendicitis, the surgeon among them operates with the tools they brought, in the room they have, on the table they have improvised, and there is no consultation with a specialist on Earth that returns in less than 40 minutes per exchange. If a crew member cracks under the psychological weight, if the third quarter phenomenon arrives, as the literature suggests it will, and one of the crew stops eating or stops sleeping or stops speaking, there is nowhere to send them. There is no couch in a familiar room they can be flown back to. There is only the same set of walls and the same 5 faces, and the calm, delayed voice of someone on Earth who cannot help in real time and who cannot come. The psychological envelope of a real Mars mission is not a soft factor around the edges of the hard biology. It is part of the hard biology. Chronic sleep disruption alters immune function. Chronic stress alters cortisol, and cortisol alters everything downstream. Bone remodeling, wound healing, insulin sensitivity, the maintenance of the same skeletal system already being unloaded by low gravity and irradiated by the sky. The mind in the whole is not separate from the body in the whole. It is the same organism, and the pressures on it stack. Mars 500 was a rehearsal in the safest possible conditions. Full Earth support, full medical monitoring, a hatch that could be opened. And even inside that generosity of circumstance, the study produced a catalogue of ordinary human erosions, the sleep, the withdrawal, the friction, that a real mission cannot afford to ignore and cannot easily solve. The people who fly to Mars will have to be selected for tolerance to conditions we have not entirely mapped, trained for durations we have not entirely tested, and supported at a distance that no support has ever been given across before. The threat is real. It is worth saying that clearly once, before turning toward what can be done about it. The pressure line, the dust, the perchlorate, the radiation, the unloading of the body, the isolation of the mind. These are not exaggerations invented to sell caution. They are the honest inventory of what the environment does to the animal we are. Every one of them is documented in the peer-reviewed literature of the last 2 decades. Everyone has an instrument or a study or a cohort behind it. None of them can be waved away by enthusiasm. But there is another honest inventory alongside this one, and it is the inventory of what human ingenuity has already begun to do about each item on the first list. There are engineers thinking about how to bury a habitat under enough regolith to cut the radiation dose by an order of magnitude. There are microbiologists thinking about the enzymes that certain terrestrial bacteria use to break perchlorate apart into harmless oxygen and chloride. There are geologists mapping the network of ancient lava tubes beneath the Martian surface, natural tunnels, some of them tens of meters wide, that might serve as ready-made shelters against everything the sky delivers. There are physiologists designing exercise regimes, drug protocols, and centrifuge systems intended to hold the human body together across the years that Mars would take from it. There are psychologists writing the crew selection instruments and the in-mission support architectures that a real expedition would rely on. None of this is finished. Some of it is barely begun. But it is the direction the honest work runs in, and it is where the next long stretch of this account needs to go. The wall is real. So is the hand that has begun, patiently, to feel along it for a door. Before we walk toward that door, it is worth pausing on the timelines that have been offered for the crossing and asking what they actually contain. Because the gap between what has been promised in press conferences and what has been demonstrated in laboratories is not a small one, and closing it honestly is the first act of engineering any real Mars program must perform. The public face of Mars ambition has, for most of this century, belonged to one man. Since around the turn of the millennium, Elon Musk has spoken about the settlement of Mars as though it were a matter of will, capital, and rocket cadence, as though the biology would sort itself out once the transport problem was solved. The early SpaceX schedules, floated in the middle of the last decade, imagine uncrewed cargo flights arriving as soon as 2022 and crewed missions following within a handful of synodic windows. Those dates slid, then they slid again. By the presentation of May 2025, the target had softened to 2029. By 2026, the internal posture had shifted further still, toward the early 2030s, and the company's public capital was flowing more visibly toward lunar infrastructure than toward Martian departure. This is not a moral failing. It is the ordinary weather of any first-of-its-kind engineering program, but it is worth naming plainly, because the same timelines that slide on the launch side tend to be reported out in the world, as though the biology on the far side had already been solved. So set the 5 walls we have walked past against the calendar and ask for each what a Mars-bound crew in the early 2030s would actually be flying with. Take the pressure line first. The Armstrong limit is not a policy question. It is a thermodynamic one. At Mars surface pressure, an unprotected human body loses the ability to hold liquid water inside its own tissues. The saliva boils on the tongue. The tears boil in the eye. The alveolar lining begins to foam. There is no chemistry that changes this, no drug that softens it, no adaptation the body could reach over 1,000 generations that would let it survive the outside air. The wall here is absolute, and the solution is equally absolute. Pressure vessels, suits, habitats, rovers, tunnels, every cubic meter a human occupies on Mars must be sealed against the sky and held above 6 kilopascals, or the person inside dies within a minute or two. The engineering of those vessels is well understood, in the sense that submarines and spacecraft have been built for 100 years and 80, respectively. The engineering of doing it for decades, with dust in every seal, is not. That is the honest state of the pressure problem in the 2030s, solvable in principle, unsolved in duration. The perchlorate wall is more interesting, because there is real biology moving against it. NASA-funded work with organisms such as Bacillus subtilis has explored whether Martian regolith can be enzymatically stripped of its perchlorate load, turned, chemically, into something a plant root could sit in without the salt reaching the human eating the plant. This is not fantasy. The enzymes exist. The pathway exists. Terrestrial bacteria in contaminated groundwater sites have been chewing perchlorate down to chloride and oxygen for as long as anyone has been looking, and the ones doing it best are already being catalogued for possible Martian use. But nothing at scale exists. No demonstration bioreactor has been flown. No closed agricultural loop that produces even a single meal's worth of clean vegetables from raw Martian dirt has been operated end to end. The direction is right. The distance is long. The dust wall has moved less. The particles are still 1 to 3 microns across. They still carry an electrostatic charge that makes them cling to fabrics and seals and instrument optics in a way ordinary dust does not. They still contain, in various proportions, arsenic, beryllium, chromium, and the perchlorate already discussed, a chemistry that would earn any terrestrial worksite an immediate shutdown notice. In 2026, NASA convened what has been informally called the Martian Dust Limit Working Group, with the explicit task of establishing what a permissible occupational exposure to this material might even look like. The fact that such a group had to be convened tells you where the science is. We are still, in the 3rd decade of the century, writing the first draft of the safety data sheet for the soil we plan to live on. Active mitigation exists on paper. Electrodynamic dust shields that pulse a travelling electric field across a surface and lift the particles clear, protecting visors and radiators and solar arrays. Prototypes work in the laboratory. Long-duration performance in an actual Martian dust storm remains untested. The radiation wall is the most quantifiable and, therefore, the most sobering to place against a schedule. The transit dose is what it is, roughly 1/3 of a sievert each way, delivered by particles that pass through aluminium as though it were paper. The surface dose is what it is, roughly 2/3 of a millisievert per day under an unshielded sky, accumulating across a nominal 500-day stay to something on the order of 1/3 of a sievert again. Sum the round trip, and a 3-year mission delivers, by conservative estimates, somewhere between 1 and 1 1/3 sieverts of accumulated exposure, a load that pushes the lifetime risk of fatal cancer up by several percentage points and, under NASA's current career limits, would end a professional astronaut's flight status. Passive shielding using hydrogen-rich materials, polyethylene, water tanks, in situ regolith piled over the habitat, is the standard engineering answer, and it works, in the sense that mass in front of a particle absorbs energy. But every kilogram of shielding is a kilogram that has to be either launched from Earth or produced on Mars, and the mass budgets of the vehicles now being flight tested do not close comfortably around either option. Wearable shielding, the Astrorad vest developed by the Israeli company Stemrad, designed to place hydrogen-rich material specifically over the most radiosensitive organs, is an elegant partial answer for transit. It does not solve the surface problem, and the gravitational wall is, at present, the wall we understand least. 0G does what 0G does. 1G does what 1G does. Everything in between is a shrug. The 2026 mouse centrifuge work suggested that atrophy could be mitigated at around 2/3 of Earth gravity, which is not encouraging news for a planet that sits at just over 1/3. Whether human bone loses 1% per month at 0.38 G, or 1/10 of 1%, or something in between that stabilizes after the first year, nobody has run the experiment, because the experiment requires either a rotating habitat in low Earth orbit or a base on the Moon operated long enough to matter, and neither exists. Against this fivefold inventory, the visions differ in temperament more than in vocabulary. Robert Zubrin, the aerospace engineer who has argued for a Mars program since the early 1990s, insists in his Mars Direct architecture that the biological problems are tractable. The engineering is essentially in hand, and the reason we have not gone is a failure of will rather than of capability. His posture is aggressive, near-term, and impatient with the analytic culture that has grown up around human spaceflight. The counter-posture, embodied in NASA's Moon to Mars architecture documents, is cautious, incremental, and explicit about using the lunar surface as a testbed, a place to learn the long-duration health and life support lessons that a Mars mission cannot afford to learn on the way. Neither posture is dishonest. They are different bets about which failure mode is more expensive, waiting too long or leaving too soon. Between the two, the space medicine community has settled into a language of its own. Dorrit Donoville, Executive Director of the Translational Research Institute for Space Health at Baylor College of Medicine, has made a phrase common in the field that captures the shift most cleanly. A Mars crew, she has observed, does not have the luxury of rapid return. The entire terrestrial model of medicine, in which a patient is stabilized, transported, and delivered into the hands of a specialist within hours, collapses the moment the transit home is measured in months. What replaces it is something the field has begun to call medical autonomy, a model in which the patient is also the provider, in which artificial intelligence guides diagnosis and procedure, in which the crew carries within itself the entire chain of care that would otherwise be an ambulance ride away. This is not a small adjustment. It is a rethinking of what it means to be sick and what it means to be helped at a scale medicine has not previously had to consider. And it, too, is barely begun. Set all of this against a launch date, and the honest reading is that the timelines routinely offered in public do not describe when humans could arrive on Mars. They describe when a vehicle capable of reaching Mars will be ready. The gap between those two dates, between the moment a Starship variant successfully lands intact on the Martian surface and the moment a crew inside one could survive the trip out, the stay, and the trip home, is not months. It is, on any conservative reading of what still has to be demonstrated, years, possibly a decade, possibly more. This is not a failure of the vision, it is the shape of the problem. The people who have looked at it longest tend to say so most quietly, which brings us underground. Of all the ideas now circulating in the Martian architecture literature, the one that keeps returning, the one that solves the largest number of the walls just enumerated with the smallest number of new technologies, is the oldest and most elemental. Do not stay on the surface, go into the rock. Mars, it turns out, has a great deal of rock available for the purpose. In the volcanic provinces of the planet, most spectacularly around the vast shield volcano Asia Mons, but also across the Tharsis Rise and the flanks of Pavonis and Ascraeus, the Mars Reconnaissance Orbiter's high-rise camera has been photographing since the middle of the 2000s a class of feature that geologists call skylights. They are dark, roughly circular pits punched into the surface, ranging from 100 meters to well over 200 meters across, and in almost every case the high-rise image cannot see the bottom. Even at the sensor's highest gain, even with the sun at the most favorable angle, the interior's read as pure black, not shadow, not dusk, simply the absence of any returning photon. Whatever lies beneath these openings is either extremely deep or overhung by walls that curve inward and hide the floor entirely, or both. What lies beneath them, the geologists are increasingly confident, is a lava tube. The mechanism is one Earth is familiar with. When a fluid, low-viscosity basaltic lava flows across a slope, its exposed upper surface cools and hardens into a crust, while the molten interior continues to move underneath. When the eruption ends and the last of the molten material drains downhill, what is left behind is a hollow tube. a subterranean pipeline of solidified basalt, sometimes only a meter or two across, sometimes very much larger. On Earth, the largest examples reach dozens of meters in width and tens of kilometers in length. Kazumura Cave, in the flank of the Kilauea Shield in Hawaii, extends more than 60 kilometers. Lava tubes are ordinary geology, in the sense that any planet with basaltic volcanism will produce them. What is not ordinary is what they can grow to on a world with lower gravity. Mars has 1/3 of Earth's gravity, and the roof of any subterranean void has to hold itself up against that pull, reduce the pull, and the roof can span a larger opening without collapsing. The consequence, in the modelling now emerging from groups such as the one led by Francesco Sauro at the University of Bologna, whose team has spent years comparing terrestrial and planetary cave morphologies, is that Martian lava tubes may reach scales an order of magnitude larger than anything on Earth. Widths of several kilometres, lengths of 100 kilometres or more, not caves in the sense of a hiking headlamp and a squeeze past a stalactite, caverns in the sense of buried valleys, long, straight, sealed-off chambers whose floors have not seen sunlight since the volcanism ended, and whose ceilings sit stably beneath tens of meters of solid basalt. Consider what those tens of meters do to the problem list. 2 meters of basaltic rock overhead reduces the surface radiation dose to somewhere near 1/3 of what it is under an open sky. 5 meters reduces it further. 20 meters or more, the kind of overburden a natural lava tube would casually provide, brings the effective dose down to something approaching terrestrial background. The particles that shower the surface arrive with tremendous energy, but energy is a currency that mass will always eventually spend. The atmosphere Earth uses to spend that currency is, in column mass terms, roughly equivalent to 10 meters of water or 4 meters of rock. A lava tube ceiling provides that mass, and then some, in a form that is already there, already stable, and already free. The dust problem is solved by the same wall. If the habitat is sealed inside the tube, the dust cannot arrive. The tube's interior, protected for however many hundreds of millions of years since the volcanism ended, holds air the settlement itself brings, and no air besides. Whatever atmosphere the crew pressurizes inside the tube is the atmosphere the crew breathes. The tube seals from the outside as effectively as any manufactured pressure vessel, once the openings are managed. And the openings can be managed. An airlock at a skylight, a plug in a chosen entry corridor, and the interior becomes, in engineering terms, an enormous natural airlock antechamber. The thermal problem softens dramatically. On the surface, the temperature cycles from roughly minus 125 degrees Celsius on a winter night to just above freezing on a summer afternoon at the equator. The same swings the REMS instrument on Curiosity has been recording for over a decade, including the drop of nearly 50 degrees across 2 sols in September 2025. Every joule spent holding the habitat at human temperatures is a joule that must be produced, stored, and rejected in the face of that cycling. Inside a lava tube, the surrounding rock buffers the temperature to something close to the planetary average. A cold value still, but a stable one, and a stable cold is very much easier to manage than a swinging one. The energy budget of a subterranean base is, by every calculation now published, a fraction of the energy budget of a surface base for the same crew. Micrometeorites do not reach the interior, dust storms do not reach the interior, ultraviolet does not reach the interior. Even the psychological environment shifts, because a room whose walls are 10 meters of solid basalt is, whatever else it is, not a fragile shell. It is a place a human mind can settle into as a place, in a way an inflatable module under a hostile sky may struggle to become. None of this makes the tube itself a habitat. A lava tube is a chamber, not a home. Inside it, the crew still needs pressurized structures, still needs closed life support, still needs power, still needs everything a surface base would need except the atmosphere of protection the tube itself provides for free. The habitat is still an engineering problem, but it is a smaller engineering problem, by perhaps an order of magnitude in shielding mass alone, and the reduction propagates through every downstream system. There is a complementary line of research being pursued in parallel, in case the lava tube approach turns out to have hidden difficulties, structural weaknesses in specific tubes, access complications at specific skylights, contamination concerns about disturbing environments that may harbour their own ancient chemistry. The European Space Agency and, in different form, NASA have both invested in situ resource utilisation studies that aim to produce a habitat shell out of the regolith itself. The concept at its cleanest is this: land an inflatable module, place it on the surface and let a set of autonomous printing robots gather the surrounding regolith, mix it with a binder, and layer up around and over the module a monolithic shell several meters thick. The shell provides radiation shielding, thermal buffering, and micrometeorite protection. It is not a lava tube. It is a lava tube built in place, out of the dirt already present, by machines that arrived before the crew did. The mass never has to leave Earth. Only the printer and the binder do. Both approaches, the natural cavern and the printed shell, share a philosophical posture, and it is worth naming. Neither of them tries to overcome the Martian environment with the energetic effort of a spacecraft. Both of them accept the environment and hide inside its own material. This is not the vocabulary of conquest that some of the public advocacy has favoured. It is the vocabulary of shelter, of finding what is already there and using it, of letting the planet do the work of protecting the crew from the planet. Which brings us to the third element on the practical list, and back to the ground itself. If humans are ever going to eat food grown in Martian soil, something is going to have to break the perchlorate apart before it reaches the plants. The chemistry, again, does not permit shortcuts. A perchlorate ion is one chlorine surrounded by 4 oxygens, tightly bound, and it will sit indefinitely in cold, dry Martian dirt without decomposing on its own. But it decomposes readily in the presence of the right enzyme, and evolution, on Earth, has already produced the enzymes we need. The organisms that carry them belong mostly to 2 bacterial genera, Dichloromonas and Azospira, which have been studied for decades in the context of contaminated groundwater at former defense and industrial sites. These are dissimilatory perchlorate-reducing bacteria, and they perform, in effect, an alternative kind of breathing. Where humans use oxygen as the terminal electron acceptor in their metabolism, the substance to which spent electrons are ultimately handed off, these organisms can use perchlorate. The reaction is driven by 2 enzymes acting in sequence. Perchlorate reductase converts the perchlorate ion to chlorite. Chlorite dismutase then splits the chlorite into ordinary chloride and molecular oxygen. The chloride is harmless, indistinguishable from ordinary table salt in solution. The oxygen is, from the perspective of a closed habitat, not waste at all but product. The organism eats the poison and exhales something the crew can breathe. The environmental engineer Robert Nerenberg, who has spent much of his career on the terrestrial application of these organisms, has put the matter with an economy that is hard to improve on. Perchlorate, he has observed, provides these microorganisms with energy for growth in the same way oxygen provides humans with energy from food. Perchlorate is a strong oxidant, like oxygen, and can therefore provide a significant amount of energy. The observation is meant to describe an Earth-based cleanup process. Read against Mars, it becomes something closer to a design principle. A Martian bioreactor in this framing is not a device that laboriously destroys a contaminant. It is a small ecology that finds the contaminant nutritious. The proposed hardware is not exotic. Fluidized bed reactors, packed bed reactors, bioelectrical reactors, configurations already in commercial use for terrestrial water treatment, can be adapted to Martian conditions with, in principle, modifications rather than reinventions. The bacteria are anaerobic, so the reactor must be sealed against oxygen. They can be inhibited by nitrate, so upstream chemistry has to be managed, and they will need to survive in transit and in operation radiation loads that terrestrial organisms have not evolved to tolerate. This last constraint has produced some of the more striking work in the literature, engineered strains that fuse the perchlorate-reducing machinery of Dichloromonas with the extraordinary radiation-tolerant chassis of Deinococcus radiodurans, an organism first isolated from meat that had been sterilized by radiation, and, remarkably, not sterilized at all. Whether such chimeras will thrive in the closed loops of a real Martian bioreactor is not yet known, but the direction is coherent, and the components exist. The point of the reactor is not, in the near term, to clean whole fields. It is to produce clean water and clean growth substrate in modest volumes, for a closed agricultural loop that never lets raw regolith touch a plant root or a human hand. Water extracted from Martian ice, run through a perchlorate-reducing bioreactor before it enters the potable loop. Regolith processed in small batches, its perchlorate stripped, its remaining chemistry balanced with nutrients brought from Earth or synthesized on site, before it is placed inside a sealed greenhouse. Food grown, eaten, composted, returned to the loop. Nothing about this is a single-step process. Everything about it presupposes a habitat willing to run its agriculture the way a submarine runs its atmosphere, as a carefully managed cycle rather than a garden. Whether it can be made to work at the scale of a real settlement is one of the questions being asked at analogue facilities such as HIC's, the Hawaii Space Exploration Analog and Simulation Site, perched at just over 8,000 feet on the northern slope of Mauna Loa. HIC's is a domed habitat set in a landscape of dark basaltic rubble that, from certain angles and in certain light, does a passable impression of Mars. It has hosted crews of 4 to 6 for missions ranging from 4 months to a full Martian year, sealed inside the dome, communicating with the outside only through a delayed link, eating what they can grow or reconstitute, working through the ordinary human frictions that emerge when a small group is confined for long periods. The project has been led since its inception by Kim Binstead, a professor of information and computer sciences at the University of Hawaii at Manoa. Her guiding metaphor for the enterprise is worth carrying forward, because it captures the modesty that the whole subterranean and biological direction requires. In a sense, she has said, they are trying to put together a toolbox for Mars, and if you have a toolbox you don't fill it up with hammers, even if they are the best hammers in the solar system. What she means, in the context of her own work, is that no single crop, no single crew composition, no single procedure will meet every need of a real mission. What is required is a suite of options, tested against realistic constraints, tuned to the specific frictions of long isolation. What she means, applied more broadly, is that the entire Martian architecture is like this. A lava tube is a tool, not a solution. A bioreactor is a tool, not a solution. A shielded vest, an autonomous printer, a delayed medical algorithm, each is one implement in a kit, and the kit is what a mission will actually carry. The soil, then, is not defeated. It is metabolized. The sky is not defeated. It is hidden from. The dust is not defeated. It is kept outside a door the settlement stops needing to open. None of this happens quickly. None of it happens in a single launch window, or a single presidential term, or a single company's roadmap. But it is coherent work done by named people, in real laboratories, with instruments that already exist. It is not the story the press conferences tell. It is the quieter story underneath them, and it is the one on which any honest arrival on Mars will eventually depend, which leaves the body itself, the animal we would be sending into the tube, into the bioreactor's care, into the shielded vest and the delayed medical loop. Because the sky can be hidden from, and the soil can be cleaned, and the dust can be excluded, and still the low gravity works on the skeleton every hour of every soul, and still the muscles unload, and still the fluid shifts upward into the skull, and still the mind carries the weight of a distance no mind has ever carried before. The body has to be held together across the years the mission takes, and how that holding might be done, the exercise, the pharmacology, the centrifuge, the drugs that have begun to appear in the osteoporosis literature, and might, one day, appear in the flight medicine kit, is the next patient portion of the account. Begin with the exercise, because exercise is the oldest countermeasure and still the most stubbornly effective one. Aboard the International Space Station, there is a machine called the Advanced Resistive Exercise Device, ARED for short, installed in 2008 to replace an earlier model whose loads had proven too low to arrest the slow leaching of calcium from the bones of long-duration crew. ARED does something quietly clever with the physics of a space where nothing has weight. It uses vacuum cylinders and inertial flywheels to imitate, at the ends of a bar, the resistance of a barbell being lifted in a gym in Houston. A crew member straps in, sets the load, and pulls, presses, squats, deadlifts against forces of up to roughly 600 pounds, around 1,675 newtons in the units the engineers use, for something like 2 hours a day, 6 days a week, for the length of an expedition. It is monotonous work. It is not optional, and it is, by every honest account, insufficient on its own. The numbers behind that insufficiency are the ones already sketched. In weight-bearing bone, without countermeasures, an astronaut in microgravity loses somewhere between 1 and 2% of mineral density every month. Say that slowly because it is worth resting inside. A percentage point of skeleton every month gone into the urine as calcium. On Earth, a postmenopausal woman is considered to be losing bone at a rate that warrants medical attention when she loses roughly that much in a year. In orbit, the same loss unspools in 30 days. Multiply out even a modest surface stay on Mars, and the arithmetic quickly turns into a body that could fracture a hip on the ladder from the lander, or pass a kidney stone in a habitat where the only urologist is a decision tree on a tablet. 20 light minutes from any second opinion. So the exercise machine is layered against, not relied upon. In parallel, in laboratories that mostly do not think of themselves as space medicine laboratories, another line of defense is being developed. Bisphosphonates, the drug class that includes alendronate, sold under a variety of names to elderly patients on Earth, taken most commonly as a 70mg tablet once a week, attach themselves to bone mineral and slow the cells that would otherwise strip it away. Clinical studies in ordinary osteoporosis have shown for years that these drugs preserve hip and spine density. Small studies in astronauts have shown more recently that combining a weekly bisphosphonate with the ARED protocol attenuates the losses further than exercise alone. That is the beginning of a stack, in the vocabulary the flight surgeons use. Exercise plus pharmacology, pulling in the same direction against the same slow drain. There is a second pharmacological family entering that stack from the opposite side. Parathyroid hormone analogues and synthetic cousins of the molecule the parathyroid gland releases to manage calcium do not slow bone loss so much as accelerate bone formation. Given intermittently in the right rhythm, they nudge the osteoblasts, the cells that build, into a slightly more energetic pattern of work. In terrestrial osteoporosis clinics, they have become part of the repertoire. In space medicine research, they are being examined as one of the ingredients in a countermeasure regimen that might, for the first time, hold a skeleton steady through the years a Mars mission would take. Anti-resorptives from one side, anabolics from the other, exercise beneath both. The picture is one of chemistry propping up a body the way scaffolding props up a wall while the mortar cures. Radiation gets its own layer, and here the vocabulary shifts from bone to biochemistry. Some of the damage a cosmic ray does when it passes through tissue is direct, a track of ionization down through the double helix of a cell's DNA, a break, a mutation, a scar that lineage carries forward. But a great deal of the damage is indirect, mediated by reactive oxygen species, unstable molecules generated in the wake of the particle, which then fan out and do their own smaller wounds to the surrounding chemistry. Antioxidants, in principle, can mop those species up before they reach anything vital. This is why radiation biology labs have spent years running rodents through dietary regimens rich in vitamin C, in vitamin E, in polyphenols from berries, in hydrogen dissolved into drinking water, and measuring what remains of their tissues afterwards. The results are suggestive, and honest researchers are quick to say they are also complicated. High doses of some antioxidants, in the presence of iron in the blood, can flip register and act as pro-oxidants themselves. Vitamin C, packed into freeze-dried meals and stored for years in the payload of a transit vehicle, degrades on the shelf. One figure that has circulated in the food systems literature suggests a loss of roughly a quarter of the vitamin's content after a year of storage, which means the dietary shield thins across the very months when the crew most needs it. So this piece of the stack is still being tuned, not abandoned, tuned. Alongside it, water-based shielding has been tested in more direct ways aboard the station. Even something as simple as a stack of moistened towels arranged around a sleep station has been shown to lower the equivalent radiation dose measurably. One evaluation reported a reduction of around 37% inside such a stack. Water is a poor material for many jobs, but it is a surprisingly good material for stopping the byproducts of cosmic rays because hydrogen atoms, light plentiful in water, are unusually effective at slowing heavy particles without producing the ugly secondary shower that denser shielding sometimes generates. The transit vehicle, in the honest architectures being drawn, is not a bare aluminium shell. It is a shell with a heart made of water, or of hydrogen-rich plastic, or of the crew's own food and waste, cleverly arranged around a shelter into which they retreat when the sun throws a flare. And then there is gravity itself, the wall against which every other countermeasure eventually strains. Because exercise can slow bone loss, but not stop it. Drugs can prop up the skeleton, but cannot rebuild a fluid distribution designed by 4 billion years of pull. What the body seems to need, what the twin studies and the rodent studies and the long expedition data all quietly point toward, is weight. Not the imitation of weight through a bar and a flywheel. Actual, continuous, everywhere at once weight, of the kind a planet provides, and a spinning habitat can, in principle, mimic. The idea is old. In 1975, a group of engineers and physicists gathered at NASA Ames for a summer study and produced, among other things, a design called the Stanford Torus. A wheel 1.8 kilometers across, spinning slowly in space, its rim populated by human beings held against the inner surface by the centrifugal force of the rotation, a full Earth gravity generated by geometry rather than mass. It was a beautiful drawing. It remains a beautiful drawing. Nobody has built anything remotely like it. The engineering problems of spinning something that large without tearing it apart, without letting its mass balance drift, without transmitting Coriolis effects into every inner ear on board, are severe. But the underlying insight that gravity can be manufactured if you are willing to rotate has not gone away. More recent concept studies, some of them worked on at Ames, some at private aerospace firms with their own reasons for wanting long human deep space presence, have retreated from the enormous wheel to more modest architectures. 2 habitat modules connected by a tether spun end over end around their common center, generating partial gravity for the crew inside without requiring the construction of a kilometer-wide ring. Sliding modules on rails, moving in coordinated ways to imitate the effect of rotation, without the gyroscopic complications of a permanently spinning structure. None of these has flown. All of them exist as documents, as models, as small-scale demonstrators on the ground. But they are being drawn, and they are being drawn by people who understand that the transit vehicle to Mars, if it is honest about what it is asking of the crew, will not be a stationary cylinder. It will be a machine that spins some part of itself for some hours a day, to give the astronauts inside the closest thing to a home their bones can recognize. The kit then, if we lay it out on a table, a resistive exercise device with vacuum cylinders and flywheels 2 hours a day, a weekly bisphosphonate tablet, and possibly a daily or intermittent parathyroid analog. A diet designed to deliver antioxidants at the moment they will still exist in the food, a shelter cord with hydrogen-rich material for the hours when the sun's plasma reaches the ship, a rotating section, or a tethered pair of modules in which the crew spends whatever fraction of each day the design permits, letting the inner ear and the cardiovascular system and the load-bearing bones remember what a floor is for. And around all of it, the ongoing coordination of the human research program, the office within NASA that carries the unglamorous responsibility of setting medical standards for deep space, distributing its work across portfolios with names like human health countermeasures and space radiation, funding the studies and drafting the requirements that will one day appear as bland lines in a flight rules document and will, in effect, decide who survives. No single element of this stack is speculative. Everyone has been built, or prescribed, or drawn in enough detail to cost. What has never been done, and this is the sentence that ought to stop us, is to run all of them together on the same crew for the length of a Mars mission in the conditions of a Mars mission. The integrated system exists only on paper. The bones that will test it exist inside people who are, right now, doing something else with their lives, which is what gives the honest mission clock its actual shape. If one takes the threat seriously, the pressure that boils blood in seconds, the perchlorate soaked through the top few centimeters of every place a boot might land, the dust that finds every seal, the roughly 1 sievert of radiation across a nominal round trip, the skeleton unloading at 1% a month, and if one takes the countermeasures equally seriously, as tools that exist but have never been layered into a single working stack, then the arithmetic of a first crewed landing is not the arithmetic of a keynote slide. It begins years before any human boards a ship. It begins with robotic precursors, landers and rovers, whose job is not to look for microbial fossils in ancient lake beds, but to prepare a specific hectare of Martian ground for the arrival of a specific crew. Tunnelers, or their functional equivalent, autonomous machines that either enter a mapped lava tube skylight and characterize the vault beneath, or heap regolith over a printed habitat shell until the shielding depth reaches the meters that the radiation calculations demand. Power systems, small nuclear reactors of the kind studied under various names in the past decade, delivered and switched on and monitored across at least 1 full Martian year before a human depends on them. Water extractors, drawing from the ice that orbiter data has confirmed lies not deep beneath large fractions of the mid-latitudes. Perchlorate bioreactors, seeded and stabilized, running their patient chloride and oxygen chemistry in sealed volumes so that by the time a crew arrives, the greenhouse has already made its first real leaves. Only after that ground infrastructure exists, verified, redundant, tested through storms and through the long winter of a Martian aphelion, does the transit vehicle begin its cruise. And that vehicle, in the honest architectures, is not a starship painted in marketing renders. It is a ship built around a radiation shelter, likely at its core, likely dense with water and polyethylene and consumables, arranged for maximum hydrogen density between the crew and space. It rotates, or a portion of it does, on some schedule the flight surgeons have agreed upon. It carries an exercise device, a pharmacy, a food system engineered against the slow degradation of vitamins, a medical bay whose autonomy the Baylor Group and others have spent years thinking through. It carries 6 people, perhaps, or 4 or 8, chosen not only for their skills but for their psychological resilience across a period longer than any submarine patrol and further from rescue than any expedition in history. The landing, when it comes, is not a triumphant plume of dust. It is, if the architects have done their work, deliberately dust-averse, a site chosen and prepared to minimize the amount of fine oxidizing material lofted by the retro rockets, a lander whose exterior surfaces are designed to shed particulates before the airlock ever cycles inward. The Martian Dust Limit Working Group convened in early 2026 with participation from figures such as David Danby of the United States Geological Survey and Brian Hynek of the University of Colorado at Boulder, exist precisely to define the standards that make that kind of landing possible, to place a numerical bound on how much dust a habitat can tolerate before it starts to hurt the people inside it. Those numbers will feed into the airlock protocols, the suit designs, the surface schedules. They will make the first sortie shorter than any Apollo excursion, and cleaner and slower. And the surface program, once the crew is inside, is not the surface program of the posters. It is subterranean. It is a rhythm of days lived under meters of shielding, work performed largely through remote manipulators and increasingly capable machines, sorties to the actual surface planned as one plans a deep dive, mission-limited, checklist-bounded, followed by long rest periods in which the skeleton and the lungs and the retinas recover. Windows, if they exist, are cameras. Sky, if it exists, is a tunable light array on a ceiling. The romance of the frontier, at least in the early years, is the romance of a mining town or a research station or a submarine. Practical, disciplined, aimed at endurance rather than spectacle. What does that reshape into when a planner runs the honest numbers? Not the 2029 landing that a presentation once promised. Not the early 2030s that a slightly humbler presentation now suggests. Independent analysts, and by and large the more conservative voices inside NASA's own architecture teams, have for years placed a realistic first crewed landing window somewhere in the 2040s at the earliest, and only if lunar infrastructure under the Artemis program provides, in the intervening years, the operational data on deep space life support and radiation exposure and partial gravity human performance, that a Mars mission simply cannot afford to be the first to gather. The Moon, in that architecture, is not a distraction from Mars. It is the prerequisite. It is where the countermeasure stack gets tested against a real deep space radiation environment for the first time. It is where the dust protocols are refined by people who can, in an emergency, come home in 3 days rather than 8 months. Say the timeline out loud, then, as an act of respect for its actual shape. 10 to 15 years of precursor robotic missions in parallel with a decade of lunar operations. A transit architecture matured against Artemis experience. A first crew, 6 or 8 strong, departing not in a founder's cinematic timeline but in a decade that current schoolchildren will enter as engineers, the 2040s at the earliest, the 2050s more comfortably, and even then that first crew will not arrive as colonists. They will arrive as the equivalent of the first winter over team at a polar station, there to prove that a small number of human beings can, with the right kit, live through a specific and bounded period at a specific and prepared site and come home again. Everything that comes after them, every subsequent crew, every incremental widening of the habitable footprint, will be built on the boring specific data those first sojourners bring back. This is the climax of the account, and it is worth naming as one, because it is not the climax the promotional footage has trained us to expect. There is no cinematic descent, no flag planting, no speech. There is instead the weight of honest specificity, the recognition that the distance between a landing on Mars and a settlement on Mars is not one launch window, but generations of accumulated practice, and that the accumulated practice is what actually matters. The founder's timeline collapses, the scientist's timeline extends, and in the extension is where the real project has been living all along, which brings us at last to the deepest frame of all, the one against which even the honest 50-year plan begins to look modest, because Mars is not, in the end, a problem to be solved. Mars is a project to be joined, and the species that would join it has, in its history, done something like this before. Consider the Andes. For thousands of years, populations of Quechua and Aymara have lived at altitudes above 4,000 meters, at pressures and oxygen partial pressures that would leave a lowland visitor gasping within hours of arrival, dizzy within days, prone to pulmonary and cerebral edemas if they stayed too long unacclimatized. And yet these communities do not gasp. They work fields, run markets, raise children. Under the skin, at the level of the genome, the reason has begun to come clear. Adaptations in the hypoxia-inducible factor pathway, in genes with names like EGLN1, that alter how the body senses low oxygen and how the vasculature responds. Not a suit, not a technology. A quiet rewriting of the chemistry of oxygen use, distributed across generations, until a pressure that would kill an unadapted human is simply the pressure at which one lives. The adaptation is not conscious, it is not fast, but it is real, and it is written in the same molecular language every human body uses. Consider the Inuit. In the high Arctic, populations have for centuries subsisted on diets that would derange the metabolism of most people on Earth. Diets extraordinarily rich in fat, and in the long-chain omega-3s of marine mammals, low in the carbohydrates the rest of the species has increasingly relied upon. And here too, geneticists have found the fingerprint of adaptation. A variant of a gene called CPT1A, involved in the transport of fatty acids into the mitochondria for burning, carried at very high frequency in Inuit populations and much more rarely elsewhere. The traditional diet, in other words, is not simply a cultural choice. It is a diet the body over generations has been retuned to burn. Extreme cold, extreme darkness, an ecosystem hostile to most human diets, met not with capitulation and not with a heated dome, but with a slow interior rearrangement of chemistry. Consider, closer to our own moment, the submariners. Not adapted at the genome, no, the timescale is wrong, but adapted at the level of practice and habit and culture. Men and women who spend months at a time inside steel pressure vessels beneath the surface of the ocean, breathing scrubbed air, eating rationed food, sleeping in bunks stacked 3 high in compartments the size of a small kitchen. The research on isolated and confined extreme environments, the icy studies, as the psychologists call them, shows that even here, at durations exceeding 2 months, mood and cognition begin to strain. But it also shows that with training, with certain kinds of attention to the inner life the crews call by names like mindfulness or interoception, the strain can be met and managed. The submarine service does not ask its people to enjoy the confinement. It asks them to endure it, to remain functional inside it, and to come home essentially themselves, and most do. None of these 3 examples map cleanly onto Mars. The Andes are not vacuum, the Arctic is not radiation, a submarine surface is, but the pattern they share is the pattern any honest reading of Mars must eventually acknowledge. Humans do not conquer environments. Humans co-evolve with them, on timescales that are cultural and technological, and, at the deepest layer, biological. The atmosphere of Mars is not going to thicken to meet us. Our chemistry, through medicine, through selection, through the slow synthesis of tools and habits, is what will meet the atmosphere. Perhaps one day through interventions we can barely picture, through gene therapies and pharmacologies and shielded genomes, the meeting will happen at the molecular level too. But even without that, the direction is the same: slow adaptation, layered practice, a relationship built across generations, not signed in a single launch window. And this is why the people whose names do not appear on the keynote stage are the ones the account has quietly kept returning to. Peter Smith, who found the perchlorate in Vastitas Borealis, Donald Hassler and Carrie Zeitlin, whose instrument on the cruise to Gale crater told us what the sky between the planets actually costs a body. The team on Insight who left us a map of the Marsquakes. Bruce Soro and his colleagues modelling the vaults beneath Arcia Mons. Bruce Rittman and Robert Nerenberg working, in fresh water and in wastewater, on the bacteria that eat chlorine. Kim Binstead, in her dome on the flank of Mauna Loa, insisting on a toolbox rather than a hammer. David Danby and Brian Hynek sitting through the meetings of a dust limit working group. Jennifer Fogarty and Dorrit Donoviel and the physicians at Baylor, building the medical autonomy that any real mission will lean on. The mouse centrifuge biologists, the lava tube cavers, the osteoporosis clinicians whose 70-milligram tablets may, one day, appear in a flight medicine kit. They are the real vanguard, not because they are more virtuous than the founders with the presentations, but because the work they're doing is on the timescale the problem actually has. Perchlorate chemistry is measured in decades of patient study. Radiation pharmacology is measured in careful animal cohorts and slower human ones. Lava tube mapping is measured in orbital passes and terrestrial fieldwork. None of it produces the images that fill a keynote. All of it produces the substrate on which a keynote might someday become true. And so, the account resolves, if it resolves at all, not with a date, not with a countdown, not with a triumphant projection of boots on red ground. It resolves in a change of posture. The idyllic render on the wall was never a lie so much as an impatience, a picture drawn ahead of the science it would require. The 5 walls the account has walked past, the pressure, the perchlorate, the dust, the radiation, the gravity, are not gates that clang open at the touch of an entrepreneur's will. They are the outline of a very long problem, one that a species learns to inhabit over generations, if it inhabits it at all. There is nothing tragic in that. There is, if anything, something restful in it. The stars have been there for 4.5 billion years. The dust on Mars has been there almost as long. Whatever crossing our species makes, if we make it at all, will be made at the pace at which chemistry, physiology, and patient engineering agree. It will be made by many people in many rooms over decades most of them will not see the end of. It will be made in the tunnels beneath Arcia Mons, and in the bioreactors in Illinois, and in the exercise labs in Houston, and in the quiet meetings of a dust limit working group whose members will never be famous. It will be made because a species that learned to breathe on the roof of the Andes, and to metabolize a marine diet in the Arctic night, and to endure 2 months of blackness beneath the sea, has always, in the end, done its adapting slowly. And if you find yourself, some clear evening, standing outside and looking up at a red point of light low in the sky, you can hold both pictures at once. The picture on the wall of the keynote, of glass domes and green lawns, is not what the next launch window will bring. But somewhere underneath that picture, underneath the impatience and the timelines and the promotional footage, the real work is going on. Bacteria are being coaxed into eating chlorine. Mice are being spun in small centrifuges. Skylights on the flank of a Martian volcano are being counted and catalogued. Pills are being formulated, tubes are being mapped. A quiet, honest, generation-long project is underway. And the red point, patient in the dark, waits.